Hi, welcome back to es346 Basic Thermodynamics. This is Module 3.1, Phases of Pure Substances. The sections in the textbook are 3.1 to 3.3. Alright, let's just go back and review where we are in the course outline. In the previous modules, we've gone through chapters 1 and 2, so now we're moving into chapter 3, which is fluid properties. Here are the three learning outcomes of this module. At the completion of this module, you'll be able to identify what is a pure substance, you'll be able to describe the three primary phases of materials, and you will understand the causes of phase change. So first, let's go ahead and define what is a pure substance. A pure substance has a fixed chemical composition throughout. So in other words, this is something that is homogeneous. You probably ran into that term before in chemistry. And the way I like to think of this, if I was to be a single molecule, and I was to look around, look over my shoulder to the left and to the right, everything would look the same. And if I was to move to another location within the material, it would all look the same. So for an example of a pure substance that we show over here on the left is nitrogen. Nitrogen, we have pairs of molecules, and everywhere within there it all looks the same. It's all nitrogen. Now, another example of a pure substance is air. Now remember, air is actually a mixture of nitrogen and oxygen, N2 and O2. However, it's mixed down at the individual molecule level. So therefore, if I was to look around, I may see a couple N2s to my left and an O2 to my right. If I was to move somewhere else, it would look essentially the same. So therefore, air is also a pure substance, although it is made up of two different molecules. Now, here's a couple other examples. First, we show water, which is a single component, but we've got it in both the liquid phase and the vapor phase. Now, this is also a pure substance because everywhere we look, we see water. Although it's more dense in the liquid than it is in the vapor, what we are seeing, the identity, is still the same. Now, an example of something that is not a pure substance would be air above liquid. Inside the liquid, we would see the liquid material. As soon as we moved into the air, we would see the air material. So that's an example of something that's not a pure substance. So sort of as a review, if you have one element or one molecule, like pure nitrogen or pure water, it's going to be a pure substance. If we have a mixture of elements, but we're in one phase, we are also a pure substance. As soon as we have more than one phase and more than one element or molecule, we are not a pure substance. Okay, so here's a question to sort of review and ask yourself. Is seawater in the ocean a pure substance? Well, the answer to that is yes. This is very similar to air, as we just talked about. So if this was my mixture of ocean water, and we have little salt molecules floating around in here, since they are completely dissolved, everywhere I look, I see more or less the same, a couple NaCl's on the left and a couple NaCl's on the right. So this is a pure substance. But we have to be careful because we have two different materials here. So this, as long as this is in the same phase, here it's all in the liquid phase. Now, as soon as I have something that is boiling, for example, it would not be a pure substance. If I was to take salt water, again, with NaCl in it, and bring it to a boil, what would come off would just be water vapor. And so above it would be just water, below it would be water and salt, and in this case it would not be a pure substance. Alright, let's go ahead and talk about phases. Pure substances have several phases, and there's three primary phases that we'll be interested in this class, and I've listed them here on this slide. So first we have a solid, and a solid has a fixed volume. It also has a fixed shape. The molecules are held very tightly together with intramolecular bonds. And although they're vibrating back and forth, recall when we talked about temperature, they're moving back and forth, they stay in relatively the same position. So there's a fixed volume and a fixed shape. Now liquids have a fixed volume, but that's about it. Their shape, that's fixed. Their shape is allowed to move around. If I move further into the gas phase, neither the volume nor the shape is fixed. It's very easy to change the volume by compressing it. Now recall when we talked about temperature, temperature was a measure of the kinetic energy. And as the temperature went up, it went up because the kinetic energy of the molecules went up. Now we know from phase change going from solids to liquids to vapors, the temperature is increasing that direction, so therefore the average kinetic energy of the molecules is also increasing. So kind of shown in this diagram, these gas molecules have much more energy than those in the liquid phase, which have yet more than those in the gas phase. All right, let's talk about phase change as we move between those three primary phases. And so we'll kind of do this as a thought problem. So over here on the left, we show water, and it's at a pressure of 1 atmosphere and 20 degrees Celsius. It's contained in this piston cylinder device that is going to exert a constant pressure. And now we are adding heat with this little Bunsen burner below it to this material. And what I'm going to do is I'm going to draw its location on a pair of axes, which is temperature and volume. And so the initial conditions may be, for example, I'll say they're just right there in the lower left of the diagram. So that would be at 20 degrees Celsius. And this would be the particular volume of material. And as I've written it here, this is specific volume, which is the total volume over the mass, which is 1 over the density. Now, as I go ahead and heat this up, energy is going to go into this liquid, and the molecules are going to begin to move a little bit faster. That would cause the temperature to go up and the volume to increase slightly. So the diagram will go up and maybe end at some point there. And this might be at 100 degrees Celsius. I have a slightly higher volume and I'm at a higher temperature. If I continue to add heat, instead of it getting hotter, it's going to begin to boil, and some of the material is going to turn into vapor. So it may look something like this, where I have the liquid on the bottom and some vapor there. Now, as soon as it goes into the vapor, it's much less dense. The volume increases very dramatically, yet it stays at the boiling temperature. And I'll move straight across, that's a straight line, to some much larger volume. And at that point, all of it will be in the vapor phase, and I'll have no liquid left. It is completely vaporized. If I continue to add heat, it'll move up in that direction. So what I've drawn over here is called an isobar, because the temperature is constant. Bar is baric, iso is constant, therefore constant temperature. Alright, we'll go ahead and switch pens here, and let's go ahead and do the same process, same thought problem again, but we'll go ahead and do it at a larger pressure. Maybe I'll go ahead and do this at 10 atmospheres of pressure. So if I start off at 20 degrees, but I'm at a higher temperature, I'm going to have a slightly smaller volume because the pressure is causing the liquid to get a little bit closer. It's a very small increase in volume, but it is to the left. If I continue to heat it up, it's again going to increase in volume to some point when it will begin to boil. Now, because it's at a higher pressure, it's going to boil at a higher temperature, and this might be, for example, about 120 degrees. Then it will boil, increase in volume. At some point, I will have completely vaporized the material, and then it will increase that direction. So I've drawn another isobar. This is the 10 atmosphere isobar, which is in the black line. The one in the bottom is in red is the isobar at 1 atmosphere pressure. Alright, so now we can go ahead and construct what's called the TV phase diagram. TV for temperature and volume. I'm drawing my temperature versus my volume. Go back in my original pen color here. And recall, we had a couple points when we went from liquid to vapor. That was like, for example, there, and then at the higher pressure was a point there and there. If I was to continue doing these experiments at all sorts of different pressures, I would end up with a collection of points that look like this. And in fact, if I was to go ahead and connect them all together, I would have what sort of looks like a little hill here going through all of the points. And this is a phase diagram where on the left, I have liquids. On the right, I have gases. And up at the point, there's a very, very top of the hill is called the critical point, where the vapors and the liquids coincide. Now recall, Going through this, I've got isobars, and I can draw isobars through a couple of those pairs. I'll go ahead and change my pen to a different color. And if I was to go ahead and draw, for example, the 1 atmospheric isobar, it may look like that. The 10 atmospheric isobar would go like that. And in fact, there's an isobar that comes right and just touches the critical point, which would be the critical isobar. Now, recall we have the state postulate which said any two intensive variables completely describe the system. Temperature and specific volume are a pair of intensive variables. So any pair of T and V occurs somewhere on this diagram. And note that knowing what T and V is, I could go ahead and find the corresponding pressure from that isobar. So essentially, I've created a map that takes a TV pair and we'll go ahead and return pressure. That's the beauty of the state postulate. Okay, let's go ahead and do a similar type thought problem that we did at constant pressure, but now we're going to go ahead and do it at constant temperature. And this one's maybe a little bit more difficult to think about, but let's go ahead and go through. So we're going to start off with, again, a piston cylinder that allows it to go ahead and change in volume. And we're holding it in a constant temperature bath. So the temperature is going to remain at 150 degrees Celsius. Think of this as just a big, giant water bath that's held at that temperature. Therefore, my material inside will always stay at 150 degrees Celsius. Now, I'm starting off with so many weights on top of my piston cylinder device. Inside here, I have water at 150 degrees Celsius and 1,000 kilopascals, or 1 megapascal. And so my point at this may be somewhere out here, up here, where I've got a fairly high pressure and a fairly small volume. Now if I begin to go ahead and start sliding these weights off, the pressure is going to drop, temperature will remain constant, the volume will get slightly larger, and I'll move downward, lower pressure, slightly larger volume, to some point at which I will begin to vaporize. Now, since this bath can supply any of the energy I need, at this point the material will boil until I end up with all vapor, and then I will go ahead and continue to move weights, and I'll move downward in that direction that way. Okay. Now, we could go ahead and do a similar thing at a different temperature. So let me go ahead and change my pens again to black. And now let's go ahead and do a different temperature. We'll go ahead and do a temperature at, say, 200 degrees Celsius. Now, if I was at 200 degrees Celsius and the same pressure, my point would be, for example, just a little bit to the right. So, same pressure, but a higher temperature. There's more kinetic energy in the molecules, allows them to have a slightly larger volume. Again, I go ahead and remove weights. I'm going to move down to some point that I'm going to boil, move across, and then move down. What I've drawn here is an isotherm. In fact, both of these are isotherms. Constant temperature. This is the 200 degree Celsius isotherm. And the one down there is the 150 degree isotherm. Okay, so now we're ready to go ahead and create another phase diagram, but now it's a PD diagram because we're plotting pressure and volume. And again, we could have pairs of liquid and vapor pressure volumes. That might look like this, and I could go ahead and connect the points. And it looks similar to what I had before, another hill. Again, I have liquids on the left-hand side. I have vapors on the right-hand side, and I have a critical point right up at the top. And I could go ahead and draw an isotherm. Let's go ahead and do that one in black. And the isotherm would look like this. It would come up, intersect, move straight across during phase change, and then upward in that direction. And again, I have a map where I can take a PD pair and go ahead and get a temperature from it. Any point on this graph is going to have a corresponding isotherm that moves through it. And no two isotherms ever cross. So I would have another isotherm that looks like this one. I'd have one below this direction, but they never cross. Okay, so as a quiz, let me go ahead and, on this old diagram on the left, I'm going to go ahead and draw a phase diagram. And then I'm going to go ahead and draw a line through it. Like that. And I want you to identify what is that red line.